So one day I saw a kid playing with a particular shape, and I said to him to encourage him, "Hey, you playing with a tetrahedron?" And he answers to me that, my teacher says it's a pyramid. And then it got me thinking about, like, what are pyramids, because I know what tetrahedron is. Tetrahedron is, tetra is for four, and head is for faces. Your face is on your head, so they're very close. So tetrahedron means a 3D shape with four faces like this. So you have four vertices also here. Vertices are O, A, B, and C. These zero dimensional corners, these points. And faces are the 2D endings of a 3D solid. So here you have four faces also. So this is one face, OAB. OBC is another. OCA, down back on the back side there is another, and down here ABC is another. So you have four faces. Also, if you can see, if you notice, 1, 2, 3, 4, 5, 6. We have six edges also, six lines. These lines, there are six edges. They are 1D ends of a volume. So six lines, but four faces, right? So four faces. It has four faces, so it's a tetrahedron. But what is a pyramid? So let's break down this word. So pyramid breaks like pyramid, right? Pyre is for fire or heat. Like pyro word, we use it many times in chemistry. For example, you have phosphoric acid H3PO4, and then its pyroform, pyrophosphoric acid. What is pyrophosphoric acid? So this is phosphoric acid molecule, and when you heat phosphoric acid, two of its molecule can condense to release water. So when you heat, water will be released in the form of steam. So that's the idea, and then you will get this pyrophosphoric acid. Okay, so pyre means pyro means heat. Pyro, fire. It sounds also the same. So pyro is heat, and a mid. So it sounds like fire in the middle, right? Well, so this does not give you any geometrical idea what it is. It is connected to something like some spiritual idea, maybe some religious idea, or something very ancient. So I may be connected to the pyramids in Egypt. So, but this doesn't give me any geometrical hint. So I took the liberty to define pyramid personally, combining what I knew about it. So then I am thinking about pyramid, and then I think about prisms also. They sound very much the same, and this word also, I cannot break it down geometrically into anything. So then I go on looking, thinking about ideas, and that's how you research inside your head. So then prism, then of course we know about this that prism. um, if you put white light into a prism, and then it disperses out into seven colors. So this is a very common thing which we have learned in childhood. By the way, this picture is from Pink Floyd's Dark Side of the Moon. So this prism, this looks like very 2D. Okay, so actually when you think about it, a prism should be like this, right? And this is you are viewing a prism from here, so you see only this part, but the light is coming here on this rectangular face, and then it disperses out inside, actually bends. All of them will bend in the same direction. It will never go like this, one in this direction, one in that direction. Sorry for that. So it will separate out, and then on the other face, this back face here, it will go there also, and then again the colors will separate out because of different refractive indices for different colors, right? So anyways, I am thinking about the shape of the prism, and then this is the shape of the prism. Okay, then I also know about these hexagonal prisms. I've heard about them, and then I also think about this parallelopiped kind of a thing, and I start to feel like that maybe these can be called prisms because they have some very interesting property. If you look at this here, this is a triangular base, and it has been extruded, and the base has been preserved, you see. So this is a triangular prism. This is a hexagonal prism because this hexagon here has been extruded and the shape has been preserved. This has been extruded like 90-degree straight up. So this can be called like a right prism. And then this is like B is not a hexagonal prism, actually it's a pentagonal prism. And also it's not extruded in right angles, so it's an oblique kind of a prism. So this kind of idea of extrusion will make us understand what is a prism and pyramid. So this idea came, and then I started looking for pyramids. So I have this tetrahedron here, of course, which is a pyramid. Then this kind of pyramids you can think of, these kind of pyramids. So what is happening here? What is happening here is like you can see that there is a polygonal base, and then you extrude it to a point, to something which you can call apex of that pyramid. Here also you have a polygonal base, hexagonal polygon base, and then extrude it to a point. Here also you have some kind of polygonal base. I don't see the other part, so I can't say. But so then I was working on GeoGebra, and then I saw this idea also, extrude to pyramid and extrude to prism. And then I thought, okay, I got it. It should be about these kind of extrusions of polygons, pyramids and prisms. Okay, so you take a hexagon and then you can extrude it to right angles, and you can get a right prism. So this is a prism, right? Right prism, because you are extruding at right angle. You can also extrude it like obliquely, so you can get an oblique prism. And then you can also have you can extrude to a point. So when you are extruding to a point, there is no right point unless and until this thing is a very regular polygon and it has a center, and then you take some point just above the center and extrude that to that center. Then you can say that this is the simplest or the right way of extruding to a pyramid. But in general, you don't have that such kind of a thing, so you can extrude anywhere and you get this is as a pyramid. You can extrude it anywhere, like also this also, right? But the idea is like you preserve the quality of the base. So this should diminish, but you should not play around with this. This is very interesting, but also in a very interesting way. We'll talk about that. So right prism, oblique prism, a pyramid, and a pyramid. But in case like if you have a regular tetrahedron and ABC is a right angle triangle, sorry, an equilateral triangle, and then this point is the centroid of the equilateral triangle, and you go straight up, and that way if you do, then you can say you get a regular tetrahedron actually, and that is a right pyramid. So pyramids can also be called right or oblique in that sense. Okay, so right circular cone, let's think about these kind of shapes, and a right cylinder. How about this? Should we call them pyramids or and prism? So of course we will call this thing a pyramid. We are tempted to say that this is a pyramid and this is a prism. Should we say that? And in terms of like cones, you can have a right circular cone, you can also have a tilted kind of a cone. But my idea is like, should we call them pyramids and prisms? So this is like when you are going, the base is circle, or so in more general words, I would like to think about like, should I allow non-polygonal bases? Should we allow non-polygonal curved kind of bases? Well, there's no problem with that. As far as we have calculus, we can do that. So in general, then your prism will look something like this. A base extruded by preserving its quality and by preserving its exact shape, not diminishing the base, by preserving the exact shape all the time, and you extrude it. Okay, and a pyramid will be in general any kind of a base extruded to a point. But there's one more thing I would like to talk about. Like let's take a look at this hemisphere. It also works in the same way. It has a base. It's a circular base, and you preserve the quality of the base. It's still circular, and then you extrude it to a point. Should we call this thing also as a pyramid? Well, this doesn't look like pyramid. This doesn't feel like pyramid, at least to me. What I have heard about pyramids, this doesn't feel like a pyramid. What is wrong here? What is missing in this pyramid? So the idea is like this extrusion is in a curved way. It's in a non-linear way. If you take a cone, then you extrude it in a linear way. You get a straight line here, right? But here you see, you get a curve. So the idea is, should we allow non-linear extrusions? So here I feel like what my subconscious connections of words inside my head tells me that here I should restrict myself and do not go into non-linear extrusions. Okay, so because if I go into that, what will happen? You will see that the sphere will become a bipyramid, right? A sphere will be a right circular non-linearly extruded bipyramid. And not only this, you will get these ellipsoids and the egg and even these stones. You can start to think of these shapes in terms of bipyramids. This is going way too general. I would love to go that general, but then how would I develop the mathematics about it? So I restrict myself there, and for prisms and pyramid, I say linear extrusions only, and I can allow like non-polygonal bases. That's okay, but extrusion should be linear. Okay, and this will give me a very interesting property. Like this is so in my head now. A prism is like this and a pyramid is like this, the most general form of prism and pyramid. So the linear extrusion will do one thing, that this formula will hold. Volume of pyramid will always be 1/3 of the volume of the prism if you are extruding it to the same height. And this I would like to discuss. So first let's think about the volume of a prism. So you have this basic volume unit. If you have a cuboid, L into B into H, you have this basic volume unit. If you want me to go into that, I can go into that, but this is, you can take it as a convention. This is how volume is defined. So let's start with L into B into H is the volume of a cuboid. So what we are going to do, we are going to more generalize this thing. This is a prism, of course. A cuboid is a prism. It has a square base, a rectangular base, and extruded linearly, right? So at least we know volume of one of the prisms, and then we can generalize from there. So you can tilt it, then you get a parallelopipe. So if you tilt it like this along one axis, you see the volume you are leaving behind is the volume you are gaining on the other side. So this again is this volume of this thing, this parallel pipe, is again L into B into H. Now notice, this is L, okay, this is B, but this is not H. This is H. This is something else, right? You can say something C. But height, by height I mean like the distance between these two planes, opposite planes. So the volume is still L into B into H. Okay, the edge length has changed, that's okay, but volume is still L into B into H for this parallel pipe. Then again you can tilt it on the other side again, and you see again you will lose some volume and gain some volume on the other side. So the volume will still be L into B into H. So volume of parallel pipe will also be L into B into H. So I'm not saying that it's A into B into C. So height is something else, okay? And but then you would say like you still you have the rectangular base. Let's this angle is still 90 degrees, right? You haven't deformed it, so let's deform it. So how do we deform it? So suppose we have deformed it, okay, in such a way that this angle is okay, no, suppose like for these kind of things, like when the angle is still 90 degree, I would go into a very interesting thing here. This is not deformed, okay, so this angle is 90 degree. So this angle, base is still rectangular. So what do I do? Like for the rectangular base kind of a parallelopipe, I would cut it into two, right? And then I would say that these two volumes are equal, okay? So then I can say that this is L, this is B, and this is H. You know what H is. So the volume of this green prism, this is still a prism. What kind of a prism is it? A right triangular prism, okay? This is 90 degrees, so I'm not I'm not taking a leap anywhere. I will give you complete proof. So this is 90-degree. So this green one is a right triangular prism, and this pink one is also a right triangular prism, and you can see by symmetry that they have equal volume. So you can say that the volume of a right triangular prism is half times L into B into H, and L is still this thing, B is this thing, but height is the height. Okay, it's not this length. It could be tilted. Okay, so we know that the volume of a right triangular prism is half into length into base into height. So right angle triangle I love because they are the queen of the geometry. And here half into length into base is going to be the area of this base, right? So from here I can say that you can write the volume as base area into height. Okay, so that's the idea. So we have base area into height, that kind of a formula for right angular prism. And then I will show you how to generalize. So a right angle triangle is the queen of geometry, at least for linear geometry. And then from here, suppose I have this kind of a prism, right? And I want to find out the volume of this prism. So this is not a parallelepiped, this is a pentagonal prism. So how do I calculate the volume of this prism? So look at the base, and I am going to divide it into right angled triangles. This you can do with any polygon. You take any polygon, concave, convex, whatever. You can very simply, if you go even random, just go random and then divide it into many triangles, and then you take any triangle and then you can cut it half into two right angle triangles, right? So if it is acute, if it's obtuse, then you can also cut it into two right angle triangles, but then the inside area will be obtained by subtracting the area of two right angle triangles. But anyways, you can always go on dividing a base into in this way, right? You can make triangles in that base, in that polygon, and then you can make right angle triangles, and then you can do the same thing above, and then you can join them. So what you get is basically this volume as a sum of volume of right triangular prisms. And let's say that these base areas are A1, A2, A3, A4, A5, A6. So you will say that the volume of prism is base area into height for all the right triangular prisms, and then you can club them in and you can say that the volume of prism is base area into height. Okay, so this you will say that this you can do for any polygon, but let's think about these curved bases prism, the more general kind of prism. How do you deal with that? So as far as you have calculus, you can cut these things into very small segments, and then you can have these parallelogram kind of area units, or you can cut them into rectangular area units as you wish. So and then from there you can build up. So you will get some inner area, and then you will get some outer area. If you take like it's about the boundaries, right? The problem is about the boundaries. So this area is definitely inside the area of this curved loop, but this triangle here, like let's think about this one. So some part is inside, but some part is outside. So you can take two limits. You can take the inside area and the outside area, and you can calculate that and use calculus, and you do more and more finer divisions. Then you would see that both of them will converge. I will show you with an example. For example, suppose this is a circle, okay, a perfect circle, and this is tilted in a plane, so like this. So you have the center, you have some chord here, you have some another chord there, and you are thinking about this area element, and this area element, you will see that it can be interpreted by an inner area and an outer area of a rectangle. So let's first say that this radius is r and that radius is r completed. Let's say that this angle is theta, this angle is d theta. You take a very thin slice. So this angle is theta, this is theta plus d theta, and then you think about this length. You see that this is in the right angle triangle. This is r, this is theta. So this length should be r cos theta, right? So r cos theta, and then based on that you take this area element, which is the bigger area element, and the length will be 2r cos theta, and this will be r dr sine theta. See, I haven't taken this length. This is very important. If you take this length, you will say this is r d theta, but this I am thinking about this linear length. So this linear length is, this part is r sine theta. It's a differential element of r sine theta, right? So that is dr sine theta, which is r cos theta d theta. These small minute things are very important in calculus. So this way I get the dA, there's some area for this element, and then I think about the shorter part and the shorter area. For that you will say that this theta has now changed to theta plus d theta. So you will have this red length as r cos theta plus d theta into 2, right? And then that length will be the same, d times r sine theta. And then you take the area element, take a look at it, pause the video if it's too fast for you, because this is very interesting. This is very important actually to understand that these two outer and inner areas will converge. So these are our area elements taken in two different ways, and then you see that as d theta tends to 0, as you go more fine and fine, these two areas will be the same, because this d theta will be 0 here, tends to 0, right? So cos theta plus d theta will be nearly equal to cos theta. Okay, so there's only one thing which you can complain about, like you're putting d theta 0 here but not here. Then everything will go to 0. Yes, then everything will go to 0, because you are taking very thin slices. But anyways, there is still some validity here, right? So when I grew up, I always saw there is some kind of glitch even there in calculus, like it's not completely foolproof. So you can say that I am being a cynic, too cynic. Anyways, so now your dA, like written right like this or this, you ignore the d theta, and then that dA is 2r square cos square theta, and then you do a simple calculation, and then you put these limits minus pi by 2 to pi by 2. If you put the limits on theta, you should cover up the whole circle, and then just check if it works or not. Yes, it works. It turns out to be pi r square. Okay, just checking it. So anyways, as far as we have calculus, we can work with these kind of curved based prisms also. So when you, this can also be explained like this, like you have these small parallelogram volume elements, and for parallelograms or any kind of Euclidean, not Euclidean, any kind of this kind of prism in which we have these straight edges in the base. So polygonal base, sorry. So any kind of prisms with polygonal bases, we have already proved that the volume of prism would be base area into height. So here also you can, with the help of calculus, you can prove that all of these volume elements will be dA into height, and that's why this volume of this whole prism would be base area into height. Okay. So now we have to think about the pyramid. So you can take a break, pause, and contemplate about what we have seen, and then now let's think about pyramid. Pyramid. Whoa! So how do you deal with a pyramid? You have this apex here. You got to take the projection of this apex on the base, just for simple geometry. And then when you take that, and then you suppose you are at any height from here, any depth from the apex, and you have same kind of the area element, and then you can draw these right angle right angle triangles, and then suppose that this is x and this whole height is h. Okay, so this length is L, then this length would be how much? So you can do simple similar triangle geometry. You can see here that the small triangle ABC is similar to ADE, and then you can take these ratios. So you will figure out that BC will be L times x by h, right? And then from here you see that this is something, this is some area which got diminished by some factor. and any length, you could take a right angle triangle in any direction, any length you would see in this area, and in the smaller area has been compressed by a factor of x by h. Okay, so if all the lengths compress by a factor k, then the area should compress by a factor of k square. What do you mean by that? Let's take a simple example. If you have a square and its edge length is 2, so this area will have an area 4, but if you take the edge length to be 1, its area would be 1. So you see the lengths, any length, even the diagonal, here the diagonal is root 2, here the diagonal is 2 root 2. So any length compresses by a factor of 2, the area element will compress by a factor of 4. So understanding that, if all lengths scale down by a factor of x by h, areas will scale down by a factor of x by h square. So that area element there is ax by h squared, and then you can take a small slice dx length, and then you can write the volume element, and then from there you can integrate, and then you would see something very interesting, this 1 by 3 appearing here because of the integration of x square. And then you have the volume of the pyramid as 1 by 3 into a into h. So a into h will be the volume of the prism here, right? Same height, you extrude it like this. You can also extrude it like this, but you go to the same height. So whatever this kind of prism is, the volume of pyramid extruded to a point will be 1/3 of the volume of a prism. Okay. So then you will see its application, like you have a cylinder. So you know about this cylinder, but this cylinder also you can think about now. This kind of cone or that kind of cone, it doesn't matter. The volume, let's say that all of them have the same height h and radius r. So for cylinder, you might know that this is pi r square h. For this kind of cylinder also it will be pi r square h. No problem with that, because it's still a prism. You have to use the height, not this slant height, but this height. And this volume is pi r square h. And for cone, you will see that whatever be the case, because it's extruding to a point, it's a pyramid, the volume will be 1 by 3 times pi r square h. You can also think about a parallelopipe like this, and then in terms of vector notation, you have a, b, c vectors, coterminous vectors, they normally call it, starting from the same point. So how do you calculate the volume of this parallelopipe? So you know that this is base area into height. That's very simple. What in vector terms, if this is a parallelogram and these are the vectors a and b, so this base area, this area here, this base area can be calculated using the cross product, because then you will get the correct height. This is the height. So the area of a parallelogram, it also uses the similar kind of geometry which we are using here. But anyways, the area is base into height. Okay, so base into height. So if you have this angle as theta, so then you will have to correct it for height. So this angle is theta, this angle will be 180 degree minus theta, and then this h will be, you can see that this h will be b times sine 180 degree minus theta, which will be sine theta only. And then you get the area to be AB sine theta, which you can write as the cross product, and then into that height. And how do you deal with that height? This height is also slant. So A cross B, the magnitude of A cross B into this height. So you can just think about this A cross B vector. This vector will be like at this angle, right angle to the base, and then you have to take the projection of C onto this vector. So you can do this A cross B dot C, right? A cross B dot C. So if you take the projection of C on A cross B vector, if you take that projection will be A cross B dot C by A cross B. But then you also have to multiply this A cross B, because this is the base area. So what you remain with, so this was the height, right? This was the height. Okay, and then you multiply it by base area, and you remain with the scalar triple product. So this is the volume of a parallelopipe ABC. And then finally you can talk about the volume of a tetrahedron. A tetrahedron is like this, and then you see if a tetrahedron, if it has a, b, c coterminous vectors. First, let's see that it's 1/3 the volume of this kind of prism. It's a triangular prism, and so the volume of tetrahedron is 1/3 of the volume of this prism. And then you can connect these two prisms together to get a parallelopiped with same coterminous vectors a, b, c. And then you can understand that the volume of prism is half of that of the volume of the parallelopiped. And then you can interpret that the volume of tetrahedron is 1/6 of the volume of the parallelopiped. So 1/6 times the modulus of scalar triple product. It's important to write the modulus here because this can give you, the scalar triple product can give you positive or negative results, but then you only have to think volume in terms of a positive quantity. Thank you.